So it's my pleasure to introduce Professor Dan Szafir, who's an assistant professor in the Atlas Institute, who has his tenure home here in the Department of Computer Science. Dan received a BA in History and a BA in Computer Science from Boston College back in 2010. And then he received a Master's of Science degree in Computer Science at the University of Wisconsin-Madison in 2012. And then went on at Wisconsin-Madison to get his PhD in Computer Science in 2015. He was co-advised by Professor Bilge Mutlu and Dr. Terence Fong. Professor Mutlu was his primary academic advisor, but Dr. Fong is the director of the Intelligent Robotics Group at the NASA Ames Research Center and was Dan's NASA mentor as part of a NASA fellowship that he had as a graduate student. Here at CU, Dan has affiliate appointments in aerospace, information science, the Institute for Cognitive Science, the RECOG Center, which is the Research Engineering Center for Unmanned Vehicles, and then the Center for Neuroscience, Culture, Language, and Social Practice. Dan founded the Interactive Robots and Novel Technologies Lab, known as the IRON Lab, where he performs research on human-robot interaction, seeking to design communicative robots that can have natural interactions with humans via a variety of modalities, including virtual, augmented, and mixed reality. He's currently working with 5 PhD students and 2 undergraduates in his lab on a variety of topics. Last year, Dan was recognized by Forbes as being a top 30 under 30 in the category of science. And just this year had 2 of his papers at the top HRI conference recognized with Best Paper nominations and a Best Paper award. Today, the title of Dan's talk is Towards Effective Human-Robot Interaction. Please join me in welcoming Dan.
Great. Thanks so much for the intro, Ken. I was going to start with a little bit of background, but I can probably go a little bit quicker through that now. So just in case you don't know me, in case we haven't met before, my group is the IRON Laboratory, which is sort of a loose acronym for Interactive Robotics and Novel Technologies. And we are over, not in this building, actually we're over in Atlas. So about just a 7-minute walk on campus. So please do stop by sometime if you're interested in some of the things you hear about today and you'd like to learn more. We'd love to have you. In general, our goal as a lab and sort of my goal as a researcher is to design robotic technologies that are able to augment human work and successfully integrate into various work practices. In particular, a few of the application areas I'm particularly interested in is space exploration, like you heard a little bit from Ken. Done a lot of collaboration with NASA, so I'm sort of interested in that, as well as manufacturing and education. And I'd be remiss not to point out that a whole lot of the work that you're going to hear about today, all of it, would not have been possible without many of the great students that work at the lab that you see here. So you'll see them sort of pop up throughout the talk as I talk about some of the different research projects that they've been involved in. All right, so let's talk about robots. Always a fun topic. So when I say robots, what comes to mind? What do people think of?
Terminator.
Terminator. Okay, good. What else?
Wall-E, Will Robinson.
Wall-E. Lost in Space. Cool.
R2D2.
R2D2, RoboCop. Okay, cool. So a mix of some good, some bad. All right. So we'll see how well I predict your answers. So the most common answer I get when I say that is C-3PO, R2D2, Star Wars. Right? It's been had a huge impact on our culture. Other options of sort of more friendly robots would be Wall-E or Data or Rosie. So, science fiction has given us this amazing vision of robots that are, these super capable assistants that are partners to humans and able to, effortlessly interact with us. Alternatively, we could Terminator first, right? This is another vision that science fiction kind of points towards, and this might be what other people think about. These are also interesting for a variety of reasons, but I'm not really going to focus on them today. My research is a little bit more focused on assistive robotics. But there's actually something missing from both these sets of pictures. Any ideas what that is?
People.
People, yes, humans. Right. So the idea is that we're building robots to solve some sort of human goal, right? And like many people, I'm really excited about how kind of tantalizingly close it seems like we are to finally achieving some of the visions that we've had in science fiction, where we can have robotics disrupt a lot of different industries. Manufacturing, space exploration, coming and working in our homes, healthcare, all these things. Just a little bit of context for this, sort of the rise in robotics. You might be following it on media and things like that. In 2005, US spending on robotic systems was about $11 billion. By 2025, it's expected to reach $67 billion. So we're sort of projecting a huge upward swing in this. At the same time, this is corresponding to much cheaper components. So in about 2010, industrial robot cost on average about $150,000. This same robot by 2015 dropped to only $25,000 in price. That's about an 83% reduction in price in just 5 years. So again, we are starting to think about achieving some of the visions that have been promised and getting robots out, working with people in these various domains. Or at least that's what industry would like us to think. The sad reality is that robots actually don't work all that well with people. Let's take a look at what happens when people try to work with robots today. So here, there's this user clearly having a lot of trouble understanding what this robot's doing, where it's going, where she should go, is it safe? Even though the system actually has this protective shell, it has some obstacle avoidance and collisions built in. What about this? And again, here I'm using robot broadly as sort of an autonomous system. So my favorite part about this is that clearly the operator is having a lot of trouble understanding where everything is, where it's lined up from the perspective of the manipulator. I just love that they just drive away at the end. One final video of interaction that doesn't quite go as planned. So again, the system is doing some pretty bizarre behavior. User clearly doesn't have a really good sense of what it's doing or why. And again, I love that you can't actually explode this. All right, so what's going on in these videos? These are just a few examples of how, unfortunately, we can build these systems, but they remain, almost, it seems like no matter how we build them, very difficult for people to interact with. And this actually is becoming more and more of a problem because as systems increase in complexity, they oftentimes become more and more of a black box to users, leaving people to wonder things like, in this video, where is this robot going? Or in this video, how do I operate this robot effectively? Or in this video, just what is the robot doing here? Right? And so, in general, the problem here is that people and robots just aren't communicating very well to each other. And figuring out and sort of addressing some of these communication breakdowns is kind of the main focus of my work. So in general, I like to think of these issues from a framework that's inspired by cognitive engineering. So cognitive engineering, back in the 70s and 80s, folks like Don Norman came up with this model for the struggles that people were having dealing with complex systems at that time, like fax machines or projectors. Of course, we still have issues with that, but control phones even, radix systems. So they broke the issues down that users have into sort of two main components that are called the gulf execution and gulf evaluation. I think it's really actually applicable to apply some of that same thinking to robotic systems. So the nice part about these models, and I'll detail them more in just a second, is that they actually give us sort of a framework for reasoning about how will people try to interact with these systems and what breakdowns might occur as they do that. So just to expand this model a little bit, it's more formally known as the human action cycle. And it sort of says that when users try to work with some sort of complex system, they go through a fairly well-defined series of steps, where first they have some goal in mind, and they have to translate that into some form of input that the system can understand. And that's called the execution cycle. And then the system does something with that input, and then the users go through a phase of evaluation where they try to figure out, did the system do what they wanted it to with that input? Was their initial goal accomplished? So I'm not going to break down all the separate steps of the human activity cycle too much. In general, what I want you to get out from this is that there's these two main spots where breakdowns can occur. On one hand, breakdowns can occur on the execution phase, where users simply just don't know how to interact with the system, what sort of input is appropriate, what sort of input can it recognize and understand. And on the other side, there's this potential gulf evaluation where the system does something and I don't know how to interpret that feedback, right? Did the system accomplish my goal? What is it doing? And does that match up with my expectations? So I think this model can be really helpful in characterizing interactions with robots, and particularly trying to figure out what went wrong in some of those earlier videos. So let's see. So basically, there's sort of two main threads in my research, one of which is focused on trying to bridge this gulf of execution. And one of the ways that I think we can bridge that is by developing new computational models that allow robots to better interpret and understand what users would sort of naturally, intuitively think of as how to interact with systems. And we can base a lot of that research on how humans naturally communicate and interact with other humans. And then we can cross this gulf of evaluation by developing robots that are more communicative in terms of what is their internal state or what is their goal, what are they trying to accomplish. And so basically, a lot of my work is sort of designed either on supporting natural interaction or developing robots that are more communicative. So those are the two main threads of my research. I also sometimes think about how can we integrate information across these threads into supporting more sort of real-world deployments and better understanding the context of real-world use in particular domains, again, like space exploration or education or manufacturing or something like that. Now, obviously, I've got way too much to talk about all these different projects today. I'm just going to instead, usually there's kind of two main ways to do this type of a talk. One is you go into one project in a lot of detail. Another is you kind of give a flyby of several different projects. I'm going to go with sort of the second strategy, the idea being I'll highlight two projects that look at natural intuitive interaction and two projects that look at more communicative robots, with the hope of maybe sparking your interest on one of them, and maybe you're interested in that and want to come talk to me later, because I'm always looking for more collaborators on this type of stuff. All right, so that's kind of an overview of the introduction. Anyway, let's move on to some projects on natural interaction. So one of the most natural ways that humans interact is with speech or natural language. And so I'm going to go over a new project from my lab that Dan Prendergast has been leading that looks at how we can develop new models of one particular aspect of natural language communication. So obviously people have thought about language, especially in the context of robotic systems, for a long time. It's a huge problem, still very open. And there's a lot of different aspects to it, especially when we try to think about applying some of the methods from the natural language processing community into embodied systems like robots, where you have to not just think about speech recognition or parsing or grammar structures. You also have to link that into some perception system where you actually have a model of the real world, and you start thinking about, well, how do I ground some of the verbal symbols that we get into real world objects? And of course, then, if you have a robotic system, robotic systems have lots of different capabilities. There's some actions that some systems can do and some actions that systems can't. So you have to start reasoning through what your robot's actually capable of as well. So again, huge open problem. There's lots of different types of work in this area. The project I'm going to talk about is sort of one small aspect of the broader context of language interaction with robotic systems. So the thing that we're sort of focused on is this idea of resolving ambiguity in language. That's something that, as humans, when we talk with other people, we oftentimes do use somewhat ambiguous phrases. So I might say something like, oh, go put that there, right? And how do we as humans resolve that? Usually we do a fairly good job at it. There's a couple different strategies we use. One is we supplement speech with other types of communication. It's often nonverbal, so things like gaze or gestures. And I'll actually talk about that type of multimodal interaction in the next project. Another thing we do when we're referring to real-world objects is we use specific object features, so things like color or size or something like that. And we might supplement that with what's known as a locative preposition. So what is the idea of a locative preposition? Let's say we had a scene like this. So we want to develop a robot that can help you out working in your garage or something like that. And let's say I want the robot to go hand me this wrench right here. All right? What would you tell the robot? What would you tell me if I'm a person? Tell me how to get that wrench.
Yeah, get the wrench.
That would not be very helpful. Well,
Left of the trowel.
left of the trowel. Excellent. Okay. So get the wrench to the left of the trowel. When I first started working these slides, my first thing was get the wrench next to the trowel, and then I realized that actually is still ambiguous as well because there's two wrenches on either side. So in general, that's the basic idea of a locative preposition. So they define where a target object is, so in this case the wrench, relative to some other reference object in the scene. In this case, we use that phrase, the trowel. And cognitive science and linguistics tells us a little bit about when people might use these locative prepositions. So in very simplistic scenes, people are unlikely to actually use these. They're more likely to use something like, if there's only one wrench, get me the wrench, or get me the red wrench if there's only one of that color. But as scenes grow in complexity, speakers are more and more likely to use some form of spatial relationship to identify the target object. So there's a few different types of categories of these locative prepositions. Generally, they're broken down into either projective prepositions, which describe some specific spatial relationship, like left of, or right of, or above, or below, or they're topological, which gives some sense of proximity, so near, beside, on. Those topological ones in particular give us a lot more difficulty if we're thinking about modeling them, because imagine something like on. I might say, this water bottle is on the table. At the same time, I might say something like, well, there's no clock in this room, I guess. I don't know if there's a clock in this room. If there was a clock, I might say the clock is on the wall, right? So we can have the same word, it's kind of overloaded into these different spatial relationship units. There's also difficulties understanding frames of reference, right? So if you said, get the wrench left of the trowel, is that from your left or my left, right? And those might be different depending on, if we're taking more of an egocentric based on the speaker's frame of reference, or an exocentric perspective. So a lot of challenges in this. We're not the first to sort of look at this idea of locative prepositions, but one of the things that we realized when we were reading through prior work is that prior models of locative prepositions often rely on fairly simplistic models that are based on the idea of ideal vectors to describe relationships. So if I said something like the wrench left of the trowel, a lot of prior systems would actually go and think you're talking about this wrench as opposed to this wrench, because this wrench more closely corresponds to that idea of sort of 90 degrees off. So they sweep vectors through space, as opposed to, in reality, in common language usage, most people would call it more, think of this wrench, where it's not based on absolute angles, it's more some combination of angles and distance and maybe other features as well. So that was something we were looking to resolve. Additionally, a lot of other prior systems, at least as they've been applied to robotics, lack support for compound phrases. So if I did something like this, the wrench on the table next to the screwdriver, one of the complications of compound phrases like this is there's two ways in this particular phrase that you might interpret it. Is it the wrench that's next to the screwdriver, or is it the table that's next to the screwdriver? Right? So you can kind of get these different potential interpretations of compound phrases, and that's something that we haven't seen a lot of prior systems address. So these were kind of two of the things that we wanted to look at and see if we can improve it. Our general approach for reasoning about locative prepositions in a probabilistic framework was to build a framework that comprised of three elements: object relationship graph, a phrase tree, and a ground score calculation. I'll go through each of those parts in turn. And one of the main contributions that we brought to the table is actually taking a data-driven approach to empirically model preposition usage by real people. And that's something that a lot of prior systems we found often use sort of heuristic parameters to tune things, versus we wanted to take more of a data-driven approach. So let me break down what each of these things mean. So first off, an object relationship graph is something that is not really new. We kind of borrowed the idea from what's known as a generalized grounding graph, which is something that Thomas Kohler, Stephanie Telix, and Nick Roy, and some other people produced about a year or two ago. The basic idea is that we're going to take a scene like this. We're going to construct a graph where nodes, every node in the graph represents one of the objects in the scene, and then edges define potential relationships between those objects. So each edge corresponds to a potential locative preposition, defining a relationship between a target object and a reference object. And edge weights are going to then encode the relational probability that this locative preposition would actually be a good way of representing this relationship. From there, we developed what are known as phrase trees. So phrase trees sort of interact with a parsing system to, if we do get a phrase like this, the yellow cube on the box next to the blue cylinder, we can build these trees that represent different potential understandings of this utterance. So here, the nodes in these trees correspond to sort of a generic noun that might be associated with a potential grounding. So here, a yellow cube, it could potentially be any of, like, let's say there were 3 or 4 yellow cubes in the scene. It could be any of them. And what we'll do is we'll then go back and refer to our object graph to actually calculate the probabilities that this yellow cube is this yellow cube versus that yellow cube or something. So again, nodes are basically these generic objects. And then we can filter these trees based on if there are specific features like color or size uttered. So we can do some pruning of our search space. But in general, we're going to construct these hierarchical relationships based on the phrase that we get, with directed edges from the root, which is the ultimate object that we want to identify, going down to the child, representing different types of relationships. We can also, so this is essentially what allows us to tackle that idea of compound phrases. And this also lets us consider the idea of different reference points. So we could also think about constructing different trees, different phrase trees based on if it's from my reference point or from the speaker's reference point. All right, so that's pretty quick through the phrase trees, but again, this, both the phrase trees and the relationship graph are sort of built off of some other prior work, so not too much novelty there. This is where the new part sort of comes in, which is that when we actually try to calculate the grounding score, grounding being, does this utterance reflect which real-world object, we can basically walk through those phrase trees in a depth-first fashion, and then we have this calculation, psi star, which is going to be our optimal grounding score. And I don't want you to pay too much attention to the equation here. The main component that we're adding to this equation is this term right here, which is the probability of the locative preposition being used that we heard based on different features in the scene. And this is actually where our crowdsourced studies come into play in allowing us to collect data to build empirical models of these probabilities, as opposed to just using some sort of a heuristic parameter or something more simplistic representation like those ideal vector models I talked about earlier. All right, so let me talk a little bit about these empirical models and how they feed into that probabilistic calculation. So again, that idea of we're trying to figure out what is the probability that a locative preposition would be used given different features in the scene. So to calculate that, we built 3 different models that essentially correspond to answering 3 different questions. So one is, what features in the scene would actually promote people using locative prepositions versus just not using them at all, just using sort of a specific object feature like color. What factors influence the selection of the reference object based on a given target object, right? So if I knew that I was going to refer to this water bottle, maybe I'll use my computer as a reference object, or maybe I'll use Sean as my reference object, right? What is the likelihood I'd use one versus the other? And then finally, what is the actual 3D geometric representation of various locative prepositions? Again, so that we can get beyond this sort of simplistic vector model and actually think about what does to the right of actually mean in 3D space? Right? Or what does on mean in 3D space? So essentially, we're able to break this term into sort of a slightly more complex equation where each term corresponds to a model that answers one of these questions. Again, you don't need to get too much down into the weeds on the particular equation. I just want to sort of give a high-level understanding of what each of these terms mean. So let me first talk about this term f sub, which is basically the idea of a spatial relationship usage model. So again, this is, will someone use a locative preposition or not? So we did an online study using Mechanical Turk to try to collect some crowdsourced data on this. So we created 16 different scenes. These are simulated scenes that contain a number of different common tools that you might find on a workbench, so like screwdrivers or handlers or clamps, things like that. And across the scenes, we varied the colors, a number of these objects, the positions of these objects. So we could create several different types of scenes. And we wanted to see sort of when would people use a locative preposition, when wouldn't they. So in this scene, maybe you wouldn't. Maybe you'd say, the idea here is that participants had to enter a phrase that would identify the circled object. So in this case, you might just say, give me the large dark clamp, right? So no locative preposition used there. Or you might say, give me the clamp next to the screwdriver. So we collected different participant phrases on Mechanical Turk to identify objects, and then we coded them for either use or non-use of a locative preposition. And then we looked at what were the different features in the scene that would predict the usage of a preposition or not. So we used PCA to figure out what the features were. Somewhat unsurprisingly, the most relevant feature was, is there a presence or not of a confuser object? So in this case here, the confuser object would be this other clamp, right? So if there's no other clamp in the scene, you could probably just say the clamp, right? And this, again, is backed by sort of linguistics research. Some of the other things that we found interesting as predictive features were the color discriminability of the object. So again, that sort of makes common sense if you think about it. Let's say there was, in this scene you could say the dark clamp, but if this clamp was also the same color, then you couldn't, then that's no longer a disambiguated phrase. As well as Nicholson contrast, which essentially corresponds to the luminance difference in these objects. So we used an FCM to create a model to predict locative preposition usage based on this data that we found. And so that would feed into our eventual model. So that's that F sub SR term. The next term I want to go over is this F sub RO term. And this essentially is getting at that question of, if I have a target object, which reference object might I use, right? Would I use my computer or would I use Java? So we used sort of a similar methodology where we created a number of different simulated scenes. So in this case, there were 72 scenes, common desk items. And we manipulated the same variables we did before, but we also added a manipulation of where the camera was and how close the camera is to the scene to get a better sense of how it this scale across different sizes, right? So if I am trying to refer to an object that's very far from me, I might use different types of reference objects than if I'm trying to refer to an object very close to me, or at least that's what we wanted to find out. So similarly, we had participants provide us different disambiguating phrases that they typed in. And then we coded for every scene, for every data point that we got from users, which reference object did they select for a given target object. So in this case, the mug was always the target object, and they were instructed to give us a phrase that indicated where the mug is in the scene relative to other objects. So you might say, well, it's the mug to the left of the box on the table, or something. So then in that case, we would have coded both the box and the table as being used as reference objects, and then the scissors and this box as not being reference objects. So we were then able to use PCA again to sort of identify which features are good predictors of when is an object going to be used as a reference object or not. And what was interesting here is that a lot of the features we found relevant were based on volume or ratios of volume. So for example, the ratio of the target object volume to the reference object volume was a strong predictor, as well as the ratio of object volume to scene scale. So that did sort of support our hypothesis that these strategies would be different at scale. A lot of our results actually indicate that people are doing a visual search of the scene, which is kind of interesting. And again, kind of makes sense when you start to think about it. And we're sort of interested in kind of connecting that over to some literature in visual search and visual pop-out patterns to try to predict about how people might use these. All right, so again, we built an SVM then to classify and sort of predict, given these features, given a target object, which object might be used as a reference object. So that's that F sub RO term. Finally, we've got this last term, which I think is actually one of the most interesting, which is looking at what is the probability that a lock-through preposition would be used based on some potential grounding here. Gamma stands for grounding of a target object and a grounding of a reference object. This is getting at what is actually in people's heads in terms of 3D geometry that these prepositions represent. So kind of similar methodology again, we developed a number of simulated scenes. In this case, these were more simplistic scenes. Every scene only had a sphere and a cube. And participants were asked to sort of identify where is the sphere relative to the cube. So there are 84 different scenes that manipulated scale, separation distance, and relative positions of these objects. And in this case, participants didn't type in a phrase directly. Instead, they rated the effectiveness of 13 different prepositions at describing the relationship indicated here. So in this case, this scene might get a high score for things like above and to the left of, but probably a low score for like below or something like that. Again, we looked at what are the relevant features. Unsurprisingly, direction was one of the most common ones, right? And that kind of gets at why even these simplistic vector models had some success, right? Because that's essentially all they're coding. But we also found a number of other features that are very important. So things like the ratio of the separation distance between the reference and target object to the reference object's volume. So that's getting at some sense of the idea of proximity, right? If you go back to that initial wrench example, I'm probably not thinking about an ideal vector relationship in my head. I might be perfectly fine with the angle being slightly off if there's a much closer object. Okay? So this kind of validated our theory that these vector-based approaches are a little too simplistic to fully model things. And what was really interesting about this is we could take our data and actually construct 3D volumes that correspond to different prepositions. So that's what this is showing. And this really kind of helps prove the point that these prepositions do mean different things to people. So something like on, clearly people use on in a different way than they use above, right? Which is itself different than using a preposition over, right? And similarly, next actually means something different than close or beside, right? And so this was kind of interesting. We hadn't seen anyone sort of develop, maybe Martha can correct me if I'm wrong, but we hadn't seen people develop these sort of 3D geometry encoded with social relationships before. This is something we're excited about. So we then, again, these were all sort of online mechanical Turk studies. We wanted to actually take this and think about how is this actually going to impact robotics. So we wanted to perform sort of a system evaluation and actually put this on a robot and test it out. So we did sort of a 10-person in-participant validation experiment. where we had people come into the lab, they were looking at a real physical scene that looked something like this, and we had them utter different phrases to identify target objects in the scene. You notice that, well, I don't know if you can see in the back, but each object has a number on it. That was so that we could tell the participant what is the target object without using a logged-in preposition ourselves so as to bias their response. So we would just tell them, give us a phrase to identify object 9. Right? And then, of course, they were not allowed to use the number in their response. In this case, we ran the phrases that we collected through 16 different configurations of our overall framework that sort of corresponded to whether we were using those features I was just describing, so whether we supported compound phrases or not, whether we were using those 3D geometries or just simplified vector-based models. So that allowed us to sort of get an analog for how would our system perform relative to other systems we'd read about in literature. Because one problem is that it's actually really hard to, not a lot of people have these systems as open source things that you just download. So we use that as a proxy for sort of benchmarking our system relative to others. And as part of doing this, we also created a new metric based on system confidence that was essential. I'm not going to go too much into it, but basically the idea is we end up with grounding, a whole bunch of different grounding scores for a given phrase in terms of what objects that phrase might correspond to. And we could do some clustering, k-means clustering, essentially, to sort of see how close are those likelihoods. So ideally, we just have one object that's super likely and a whole bunch of very unlikely objects, right? That's the ideal scenario. But sometimes the system might be less confident, meaning we have overlapping clusters, we have less discriminability in sort of our grounding calculation. And we'll talk about that in just a second. In general, this just shows, again, there were 16 different configurations. I'm not going to show them all here. This is sort of just looking at sort of the baseline system that uses the vector-based model and doesn't support those compound phrases versus our full model that does everything I've talked about so far. You can see we have a big win in accuracy. And in particular, the two things when we looked at all the different combinations that really seemed to improve accuracy was looking at those empirical 3D geometries and being able to support compound phrases. And we found those were huge differences, both in our accuracy as well as in that underlying system confidence. So let me show a quick video of what that looked like. Unfortunately, I think the audio is only playing from my laptop, so I'll try to repeat it if you can't hear it.
Robot, point to the cube in front of the box on the left.
So that's sort of like a baseline system. It couldn't handle that.
Robot, point to the cube in front of the box on the left.
Of course, cheated there because he could have just had the right cube. It's going to go through two more examples, and I want to call out the last one.
Robot, point to the cylinder on the rightmost box.
So older systems had trouble with topological prepositions.
Robot, point to the cylinder on the rightmost box.
And usually that's because it's hard to figure out what a vector relationship of a topological preposition would be.
Robot, point to the yellow pyramid to the right of a yellow cube.
So in this case, the older model actually works. It gets the correct answer. But the idea here is that it actually was kind of guessing between 3 different candidates because there's 3 different pyramids in the scene.
Robot, point to the yellow pyramid to the right of a yellow cube.
Versus, so with our system, the system is much more confident, and there's actually only one object that it kind of knows that it is. So it knows that those other pyramids are definitely not what you're talking about. So just some takeaways from this project is that we can create these empirical models of locative preposition use, which is something we're very excited about. And we found again that compound phrase support is really critical if we're going to work with one of these systems in practice. So there are a bunch of next steps for this work. One limitation of this is that we were cheating in that we already knew where all the objects were, so we weren't using an online perception system. So we'd like to integrate that with an online perception system next so that we could actually think about more dynamic scenes. As well as, again, there's this idea of some of these prepositions like on are kind of tricky. Our current system sort of works for that, but I think there are better models we can construct for some of those potentially overloaded prepositions. And one of the big limitations is that this is all based on a single utterance. Real interaction doesn't look like that at all, right? In reality, you have a dialogue back and forth with people, and you reference resolution. So we're looking at ways of sort of incorporating more of a back and forth type of model into our system. So that's that on sort of natural language, or one small aspect of natural language that we're looking at. I mentioned before that, of course, there are other types of cues that people use, and we communicate in multimodal fashion. So we're also looking at this. This is some work that Connor is going to be presenting at IROS next week. So one of the things we're interested in terms of thinking about multimodal cues is that they provide supplemental information oftentimes to speech. And we were kind of thinking about, well, when might that be most helpful for a robot? And we thought that one of the places that robots currently really struggle at is working in unstructured environments. So most robot usage nowadays looks like the top picture here, where you have robots sort of in factories, where you have a very structured task, a structured environment. You can sort of nicely encode exactly what the robot's supposed to do. But we're all interested in getting robots and having them work more in unstructured environments. So I have this Iron Man example where he's prototyping this, and obviously in Iron Man 1 he's got these robots to help him. There's no way on Earth that those robots could know what he's trying to do, right? So how they help him is amazing. So this is the type of thing where we're thinking, well, if you don't have some sort of like hierarchical task plan embedded in the robot, are there ways that we still might be able to provide some form of assistance? And so our idea was, what if we do some multimodal observations about what the human's doing, and see if we couldn't, even though we don't know what the overall task is, maybe we can recognize sub-pieces of the task that might be common across many types of different activities. So for example, in this idea of sort of assembly or sort of warehouse type of tasks, or even if you're just like at home prototyping or working in your garage, there might be common sub-themes that you might see, like fastening pieces together or lining things up or searching for parts. And maybe we can recognize those types of activities and provide some assistance there. So we had people come into the lab, and again, we kind of took this data-driven modeling approach. So participants came to the lab and they completed an assembly task with the help of experimental amplifier, so just another person that was helping them out. So we identified a few different common types of things that people do. So this is the idea of fastening. That's one example. Connecting parts is another. So that's sort of like what connecting parts might have looked like in the data collection phase of this. And then, finding, let me see if I can put it. There we go. Finding parts or searching for parts might have looked like something like that. So we built sort of a subtask recognition architecture where we used sort of deep learning approach to train different networks across different features. We looked at audio features, body pose features, and body movement features. And I'm not going to go too much into this. Essentially, we eventually created an ensemble system that allows us to fuse the estimations from each of these subnetworks to form an overall subclass recognition. And then we put that on a robot, and we had people come back to the lab, and now instead of working with a human partner, they worked with a robotic partner, and they did a completely different task, although still within the realm of assembly. We looked to see, in this new task, could the robot actually recognize when participants were doing some of these subtasks, and thus help out, even though it had no formal task model. So we had two different conditions in this experiment. In one condition, which is called kind of the command-driven assistant, users just had an iPad, and with buttons on it, so they could just say, like, robot, give me more screws, or robot, give me more nuts, or something. And in the other condition, participants still had that iPad. They could request things whenever they wanted, but the idea was that the robot would also try to classify what the user was doing online and proactively hand them things the robot thought they might need. So a quick video of what that looked like. And in this case, the training examples are interspersed, so you can see that really the training and testing environments were quite different. They were doing a different task. The lighting conditions are different. The camera recording conditions are different. To try to sort of minimize any potential for process of contamination there, to really see, like, could this actually work in practice? So this is what an accurate classification of the fast may look like in the test phase. You can see he's kind of smiling at the end there. So those are always the rewarding ones, not when like robot drops the cup or something. So we have it all. I'm going to kind of skip through the results just for time. At a high level, we were definitely outperforming chance in terms of our recognition. Obviously, there's a lot of ways we could improve our recognition for a real system. This is almost more of a proof of concept of could we do anything if we didn't have a formal task model, and we can. Unsurprisingly, people found that proactive systems have much more perceived agency. In usability, they actually rated the robot the same, possibly because they could accomplish a task either way with either assistant. But what's interesting is when we actually modeled usability across which predictions the robot actually got right, we found that if you got the prediction wrong and you handed the user the wrong thing, that actually hurt the interaction a lot more than getting the right thing helped the interaction. So it kind of indicates that we need to be a little bit conservative when we're designing these systems. And again, it indicates that systems really need to have something like an internal confidence metric, like the language system that Nakato did, so that we can sort of avoid these like very unhelpful and deleterious types of interactions. All right, so that's kind of the takeaway there. Went back through that one a little bit quicker. But that's kind of two projects along this theme of supporting more natural interaction to help people interact and sort of convey their goals to a system more effectively. So in the last 10, 15 minutes, I'm going to go through two more projects, again, at pretty high level details about designing more robots that are more communicative to people. And again, the idea being here, if we can design robots that are more communicative, it can help people cross this gulf of valuation. And in particular, I'm going to talk here about some work that I've found pretty exciting, where we're actually looking at how new technologies in the form of augmented reality can actually help people and robots communicate better by showing people information about sort of what is a robot trying to do, or what is its internal state, things like that. Just as background, a lot of this work, this is a lot of the work that has sort of come out of my collaborations with NASA. So this over here is Astrobee, which is a new robot. It's going to be launched on the space station hopefully in November. Knock on wood. It's been pushed back, I think, 4 times now. So hopefully it'll be launched this time. And NASA's really interested in, this robot's going to be sharing not only the working environment with the crew, but that's also their living environment. So it's really important that the people in the robot are able to sort of work effectively with each other. And so they're very concerned about how we might communicate all these different types of information that astronauts might need to work with the robot. Of course, there's lots of different ways that robots might communicate information. Some of my past work has explored some other aspects of things like nonverbal communication, like robot motion, things like that. Again, today I'm going to be talking more about this sort of new thread of research that looks at how augmented reality might be used to communicate this. So this is some work that we presented at HRI this past year that Michael, Iman, and Jen, who's a master's student, worked on. And this is really aimed at solving that problem we saw in that very first video. This is known as the motion inference problem, which is the idea of, can I understand where this robot's going, or not even a robot, can I understand where another agent is going relative to me, so that I can feel safe around it, that I can plan my own actions. So the question here is, can augmented reality, or how might augmented reality support this type of information exchange? And we sort of thought about, well, what are the key things we might want to convey to users about motion intent? Things like, when is a robot, what is its ultimate goal, when is it going to get there, when is it going to leave, what path is it going to take, what velocity is it going to take, things like that. And we kind of combined that with sort of an overall design framework as we thought about these augmented reality technologies in terms of what types of support they can provide. So we thought about, well, we could use augmented reality to put new cues sort of in the environment itself. Or we might use augmented reality to change some aspect of the robot itself rather than the environment the robot's in. Or we might take inspiration from sort of heads-up displays that pilots use to actually give the user a new interface and give new information there. So we sort of looked at sort of prototype designs that sort of sample from all these spaces. So I'll show just a quick video on each of them. First design we call nav points. So in this we have sort of the robot's flight trajectory interspersed on 3D space. these radial timers, the inner radial timer that's white tells you when the robot's going to reach that waypoint, and the outer blue radial timer tells when the robot will leave. And we have these kind of like dots going through to give you a sense of what its velocity is going to be. So that one has a lot of information on it, so it might be too much information actually for people. So we looked at a more simple design. So this design is simply an arrow that extends from the robot X number of seconds in the future. That's just a parameter that we chose. I think we ultimately went with something like 8 seconds in the future. But it sort of encodes some of the same information, but at more of an abstract level, as opposed to a more low-level precision that we saw in the previous design. A different idea, again, is that instead of augmenting the environment, we could augment the robot itself. So this design looked at drawing on human perception of gaze, which is a very powerful cue. And so we went as triggering of gaze as we possibly could. So one of our initial prototypes was more about just adding kind of small eyes to the robot. And eventually we decided, well, let's go big or go home. Right? So let's see what the maximum effect we might have. And then finally, we looked at sort of more of a utilities design, kind of inspired from things like radar. So in this case, you always have this radar system that tells you where the robot is relative to you. So this gets more relative location rather than absolute. In addition, it's really hard to see. It's really hard to record these things, it turns out. You can't really see it here, but anytime the robot's not in your field of view, you get an off-screen indicator that shows basically an arrow pointing out where the robot is relative to your field. So we have these 4 different designs. We brought people into the lab with 60 participants and sort of had them do a task where they had to share an environment with this robot and share different workstations with the robot. The idea being that if people could better predict where the robot's going to go, they could plan their own actions better and be more efficient in their task. I'm going to kind of just cut right to the chase here. In general, all these designs perform better than the baseline. Baseline is a system that simply, you don't get any augmented reality feedback. There's basically just a defined front of the robot, and the robot will sort of always orient where it's going to go next. So all these systems allow people to plan their own activities more efficiently and sort of be interrupted by the robot less. And in addition, there's a lot of sort of subjective benefits to these different designs in terms of how people viewed the robot, whether they thought they had a good sense of where it's going, whether they'd want to use it. And at a high level, the idea here is that we were really excited that we sort of showed that augmented reality can be used to convey new types of information to users, sort of make information that might be sort of hidden more visible. And so actually what was interesting is that the very first design was our best performing one. So this is something where Michael and Human were right and I was wrong. I thought that was going to be sort of too much information for people, although I still think it will not scale as well as some of the other designs. So the jury's still out on that. All right. So let me see. For time, let me skip ahead a little bit. I'm going to skip this next project, although I'm happy to talk about it later. So let me just skip ahead. There's one other project I kind of want to talk about. Too many seconds. So the last project I want to talk about is thinking about, again, augmented reality. So that other project that I just kind of skipped through was another take on sort of how augmented reality might be used to support users in crossing this kind of gulf evaluation type idea. As we were working on both these projects, we started thinking, well, this has been a really useful tool in sort of presenting new visual information to people. Could we also use augmented reality technologies to help think about how we might cross the gulf of execution issues and actually design new control or command interfaces for these robots? And so this is a new line of work that we just submitted the other day to HRI, so this is under review, that uses a paradigm that we're calling virtual surrogates. So the idea here is that instead of directing input directly to a robot, which is how traditional collaboration systems work today, we could instead sort of hijack user input and direct it instead to a virtual representation of the robot that the real robot is going to then mimic. So this allows us to sort of pilot around a virtual robot and sort of see how it interacts with the environment, and hopefully then correct any actions that we don't like prior to the physical robot actually doing that, crashing or something like that. So there's kind of 2 control systems we developed. One is called real-time control, in which the virtual surrogate acts almost as like a magnet to the real robot, and the other is more of a waypoint basis. So probably the easiest thing to do is just show a video of how these work. You can ignore these columns and numbers. Those are part of the experimental task. So the idea is that participants had to go and navigate the robot to these different zones to collect and analyze data at the different zones. So that's what those cylinders are representing. So this is, you can see the virtual surrogate kind of acts as a magnet for where the real robot would travel. And alternatively, we can add more delays and actually create a waypoint-based system. And waypoint-based systems are very common in robotics. It's just that traditionally you would have to use some form of traditional display, like a computer or a desktop or something, to actually plan it. So your planning is separate from the real-world operation that you're going to use the robot in. So it's much harder to sort of intermix those physical cues. This just gets into, you can pause and edit the waypoints and things like that. So we did an experimental evaluation of this. Again, you're probably seeing a theme here. Typically, I'm an empiricist. We will do some sort of experiment to evaluate our results, see if the things that we build are any good. In this case, we had participants use both baseline, which they just use joysticks, which is a common way that these robots are operating today. And then they also used both the real-time and the waypoint surrogate designs. This was a within participants experiment, so every participant used all three designs in a counterbalanced order. And then additionally, after they had used all three designs, there was one fourth round where there's a button and users could switch at will between any design. So we wanted to sort of see objectively what would their preference be. And in this case, we tried really hard to include in our sample population more expert users. So we recruited 7 users from a local CU drone club to see, would they actually like this system given they're already very experienced at essentially the baseline joystick control system. Just in general, both the surrogate systems allow people to complete the task much faster, as well as they had to do some secondary tasks as well. I didn't go into that, but they were able to sort of respond to new things more quickly. This is, I think, the most powerful result, which is in that fourth trial, when users could use whichever interface they wanted, what did they use? Not a single person used the baseline system for even a second. So before the task started, they had switched to one of the other systems, including all the expert users. So they liked our new system much more so than the systems which they were sort of familiar and expert at. So I thought that was a pretty powerful result. So anyway, the takeaways of this one is that these surrogates are sort of, maybe hold promise in designing new control systems, and that this AR type of work can support not just gulf of execution, or not just gulf of evaluation, but also gulf of execution issues. So we think it's being able to combine this augmented reality technology and robotics be a really powerful way forward for users. And that's kind of been an exciting new thread that I've been having a lot of fun over the past years exploring. So I'll pretty much end it now. I did mention, by the way, that we do some other work in our lab that thinks about integrating some of this knowledge for specific application areas. So unfortunately, I don't have time to talk about any of this really, but this is some work I'm doing with a lot of fun collaborators. So we're doing some work looking at space exploration and telerobotics with Jack Burns, Nisar, and Torin. We're doing some work with assistive technologies with Sean and Darren. One of the things I'm most excited about actually right now is that Chris, Danielle, and I just got a medium to look at taking some of these technologies that we've been working on, integrating augmented reality robotics, along with some of the visualization systems that Danielle builds, and some of the robotic perception systems that Chris builds, putting that all together and getting that out in the field so that emergency responders doing things like wildfire fighting and maintenance could actually use this. So you can imagine, they might send a drone up to do some scouting over the ridge or keep track of burn lines. How can we use all of this to sort of direct information back to them so they can really improve their practices? So that's something we just got funding for, so I'm really excited to start working on that. But that was kind of a whirlwind tour through some of the different projects that my lab is going on. Maybe something caught your eye. If so, I hope so, because come talk to me. Again, I'd love to work with other folks. All these issues are much bigger than I am. And again, I'll thank all the students that make this possible and some of my collaborators up here. Thank you. Happy to take any questions.
So when you were talking about the one of the AR displays, I'm trying to remember which one it was. You said that there was a decrease in time. It was the first project you were talking about. Was that the time for the robot to execute its task, or the time for the human to execute
The human. Time for the human.
Okay.
Yeah, in that case, the robot was sort of on a fixed path. So we weren't really caring about, the robot was sort of just simulating actions. We were more looking at like, how did this affect the user? So yeah, that was user time. Yeah, I know I went through those results really quickly, so sorry about that.
I saw that you used the HoloLens.
Mhm.
How did you make that choice?
At that point, when we did some of those experiments, it was essentially either that or the Meta 2 were the only ones on the market at that time. And the HoloLens just seemed to offer a few features that were more, made it easier for us to develop on. Nowadays, there's some new ones. There's, the Magic Leap. Maybe we'll buy that. I don't know. The reviews so far haven't been great in terms of it seems similar in capability to HoloLens. Really what we want is HoloLens 2. We just bought a new system in our lab called the Z Mini, which is a stereo camera that you put on top of something like a more traditional VR headset, like the Oculus Rift or HTC Vive, and that allows you to do video-based pass-through AR, as opposed to the HoloLens, which is just passive pass-through AR. So we're actually doing some other projects. I didn't have time to chat with that, because that allows you to do different things. One of the issues with passive pass-through AR is that you can never make anything darker, right? You can only make things lighter, and so things are able to see through. But with video AR, you don't have that issue. You have more full control of the scene. On the other hand, sometimes you have more delays, right? And any delay can cause sickness and things like that. So the Z Mini is actually pretty good. So if you haven't used that, I'd recommend it. But yeah, it's just some different devices we're using.
Yeah, in that last scenario where the traditional method in the LP stuff, where the traditional method had a high degree of uncertainty, how would you communicate that, and is that something that you're going? So in other words, a natural reaction for a human would be which one?
Yep.
Or can you give me some more disambiguation?
Yep, exactly. So that's actually what we're working on right now as a follow-up experiment, and that gets to also that idea of, in the real world, you don't just utter a single phrase and you're done. Exactly as you said, you have a dialogue to do reference resolution. So that's what we're extending our model to do right now, where if the confidence is below a threshold, our current approach is just to point at the one it thinks it most common, like, do you mean that one? And then if not, they say another phrase and we'll try to parse that and update our confidence metrics. But yeah, we haven't explored that yet, so that's what we're extending our system to be able to do right now.
It's interesting, there's no interaction between the position of the human and the position, the cognizance of the robot, and the human position in terms of talking about direction.
Yeah, so that gets at the idea of frames of reference. So if I'm a human and I'm speaking to a robot and I tell it to go get me the thing on the left, is that sort of from my egocentric perspective, or is that from like the robot's exocentric perspective, right? So as humans, there are a few different ways that we resolve that. Sometimes we use gestures, so we might point, and then that makes it unambiguous. The way we are calculating our phrase trees allows us to create a tree for every different possible frame of reference, and then we can calculate which is most likely. And that's sort of the approach we're going with right now. But there are probably better approaches out there. And so that's something that if people have suggestions on, I'd love to kind of think through more. And I wouldn't be surprised if the NLP community has a better way of thinking about that. So, but that's exactly right. Yeah, there's absolutely different frames of reference we have to consider for actually doing this. Because even as humans, we have that problem sometimes, right? We don't always know. Okay.
Not better. We don't have a better way. Just, alternative representations for all the, possible interpretations, and you have to figure out which one. This isn't really a technical question. I'm in the middle of a DARPA program called Communicating with Computers, and we're doing all this stuff with building structures with blocks. And it's all about spatial transitions and dialogue and all this other good stuff. So would you like to talk about that?
Absolutely. Yes, we should talk. Excellent. So it's 4:30. I'm happy to stick around if folks have other questions.
Please join me in thanking Dan.